I'm going to share my screen now, and I hope you can see it well. Is this the correct screen? Sorry if I need a second. And here it is. Yes, it works perfectly fine. So it's a little bit hard. Please excuse me jiggling around with my slides here and my environment because doing the moderation and doing the talk at the same time isn't that simple. And I hope it will turn out nicely. So let's dive right into it. The next talk, the next, I don't know, half an hour or however long it will take us. If you have any questions, please send them in the chat. I will try to monitor the chat window here. The next talk will be, I call it constant fun with Rust. My personal background is very much in managed languages like C Sharp, and I did a lot of TypeScript development. I did a lot of Go development, and in the last few years, I focused a lot on Rust. And one of the things that struck me when I started to work with Rust was the possibilities that you have when working with consts, when working with constants, and especially when working with constant evaluation in constant functions. And this is exactly what I would like to do today together with you. This is a beginner-friendly talk. So if you are rather new to Rust, or if you have already a little bit of Rust knowledge and you would like to deepen your knowledge in this specific topic, that's exactly correct. That's exactly the right talk for you. So let's get started. I have no slides. I will do some live coding, but I have prepared a lot of samples. So you will see me copying some code in, but we will also do some live coding here. So let's get started and get right into the basics. First, it's very simple. So if we have, I don't know, something like this, nearly the answer, we can define consts as you obviously know them from other programming languages. That's very, very obvious. And then we can, I don't know, use these consts and use them in order to build additional consts. Here you see them, answer, nearly the answer plus one. And then we can take this one, let me copy in some code and print it on the screen. I mean, that is obvious. I don't have to talk a lot about it. Obviously, this thing here will be evaluated at compile time. This is definitely possible. And you can write a lot of things on the right-hand side of this equal sign, of this assignment of the const. But not everything is allowed in a constant expression. I will share at the end a link to a sample code where I have the samples that I showed here, but with a lot of documentation comments. And there you find a link where you see all the limitations that you have on the right-hand side. But a lot of the things that you would expect here are simply there. Rust is not just capable of doing numeric consts, of course. What you can also do is you can add, for instance, a constant string, and that would look like that. Let me put in that here. That is just a constant string, nothing special, works like a charm. We also can use constant arrays, something like this. Let me put that one here. We can do that, absolutely no problem. Works, oops, sorry, should be here, works like a charm. So this is what you might expect when you come from a different programming language. This is what you already know. Let me surprise you with the first slight small things. Consts in Rust do not need to be declared on the top level. You can declare constants in Rust wherever you want. Wherever you want. You can, for instance, define, let me show you that here, you can define a constant in the middle of the main method. This constant now has a scope. It's scoped to the main method, and we can only use it within this method. Keep that in mind because in a few minutes, we will need that. We will need that because we will find out that scoped constants have very specific properties and capabilities, and I will show you how this works. So this was the basic stuff. Check, first lesson, done. This is the usual const stuff with a little bit extra. Now let's take a look at more interesting samples. First one is I would like to show you that Rust constants don't need to be basic data types. We can, in fact, use more complicated data types. Let me copy in some code here. This is a customer object. This customer object has a string in it and an age in it. And now I would like to define a constant customer. For whatever reason, I might want that, but I'm definitely capable of doing that. I can define here a constant customer, and I can use the struct that I used before. And this definitely works. Let me show you that. I can add a print statement here in order to get rid of the warnings. And now we have a constant customer. So structured data types can definitely work as constants here. That works nice. Let's enhance this sample even further. What if we bring back some constants that we had before? I had this text and the numbers before. Now, could I use another struct I called here named numbers, and when I declare the constant struct named numbers here, can I refer to the constants up here? Yes, I definitely can. So if you have constants, in this case, I have a string and I have an array, you can always refer to these constants and get the address, get the reference to these constants. So with this, we create a named numbers constant, which is a structured data type where I use a constant text as the name and a constant number array here at this member. This works perfectly fine, and I can prove that to you by copying here into the main method. You can try all these things yourself after this talk. I can copy it in, and it works perfectly fine. I can iter over the named numbers. It will get me the correct sum. Trust me, I will not run the program because you will probably guess what the result will be. So this is kind of surprising already. But let me surprise you even more. For that, I'm going to clean up a little bit here. Let's get rid of that one. And let's add a trait. This trait here. I call this trait has numbers, which has a constant numbers and a constant last number with a value inside of a trait. That might be even more surprising for you. Yes, a trait is something like an interface, very similar to what you know from an interface from other programming languages. But in this case, we can have a required constant, an associated constant, a constant associated with the type implementing the trait. We can have that requirement inside of the trait. The second one is very similar. It is also a constant, a requirement on the trait, but we can provide a default value already in the trait. Now let's create a structure. I have numbers, here we are, and implement the has numbers trait for I have numbers. And that works perfectly fine. We can now fulfill the trait by adding an associated constant to our type, I have numbers, and provide the value that we want to have for this constant. We can even override the default value. I've prepared another struct with another interface implemented with another struct, a trait with another struct here for you. Here you see I have the type I have other numbers, and in this case I'm implementing the existing has numbers trait by overriding the default value which came before directly from this trait here. Here, I'm overriding the default value for the constant inside the associated type, and I can immediately use it as you can see here. And that will give me an array containing 1, 2, 3, 4, 6, because I've overridden the default value of the constant from the trait. So keep that in mind. Traits support consts. The consts that you saw before are free constants. They are not associated to a type. But here we have consts associated to a type. In this case, the type I have other numbers. And those consts can be required by a trait. So maybe you have learned something new about Rust that you don't know from other programming languages. Next chapter, check. let's go into the next topic. Another thing that is possible with const that you might not expect from when you come from other programming languages. Let's define a very simple structure here. This one will say goodbye, and you maybe can already guess what will say goodbye does. Will say goodbye, as you can see here, is a struct which consists just of a string. It contains a string, and that will be the goodbye message. Now let's implement the drop trait for will say goodbye. The drop trait does nothing more than just printing out the goodbye message that we passed into the will say goodbye structure here. Now we can do something interesting. We can say, hey, let's take this constant here, one, and define it here. Constant goodbye in German. It is of type will say goodbye. And we say will say goodbye auf Wiedersehen, which is the German version of goodbye. And now we can use this constant inside of our main method. In this case, I'm putting it inside of a scope. So what will happen here, we will copy, because consts are by default copied, and we will see that later on, we will copy the will say goodbye constant here. And this constant, the type of the constant, has, in this case, a kind of destructor, and it will print auf Wiedersehen on standard out because the variable goes out of scope exactly here. So as you can see, constants can have destructors, and if we use it like that, they will be executed. Okay. So interesting thing. What you see is that we are reaching a point where we will see that consts in Rust are not just constant values, but they essentially contain code that is executed at compile time. And the next example that I'm going to show you goes into exactly that direction. Let me get rid of that one. As I said, I will share the GitHub link of the whole example at the end of the talk, so don't worry. It will work just fine. Let me see. Yeah, here we are. Let's add some code. This has nothing to do with consts. It is just the thing that we had before, has numbers. Yeah, we saw that code before. I have numbers. Yeah, we saw that code before. Now imagine we would like to write code, a kind of test that verifies that I have numbers implements the has numbers trait. How could we do that? Well, I have a bunch of interesting things for you here. First, we can define constants which don't have a name. They are anonymous. We can use this discard operator, the underscore, to tell Rust that we don't need a name for this constant. You might wonder now, why should we create a constant without a name? If the constant doesn't have a name, we can never ever refer to this constant because it doesn't have a name. That's the whole point of it. It will get even stranger before it makes sense. Let's define the type of this anonymous constant. And in this case, I make it a unit. I make it a unit, so with this, it can just have a single value, the unit. That doesn't make any sense, right? We have an anonymous constant which just can contain a single value, the unit. So let's assign here a value for this constant, and we can do it exactly something like this. Okay. So this will now be code. This is a code block that runs and returns a unit to assign it to this unit to a constant which doesn't have a name. What is the whole point of that? The whole point of that is, let me zoom in a little bit, that this code is running at compile time, not at runtime. And that's the whole magic which goes into constant function evaluation, which is the next big topic that we are going to talk about. So what we can do is we can add any code here, not really any code. There are some limitations, so you can't write any code at that point. I will show you some limitations later on, but we can in general write nearly any code and execute it at compile time. So here I have prepared some sample code here. And this code will now just use, as you can see here, this struct implements my trait, which uses the has number trait here. And then we will take the I have numbers, and with this code using the phantom data and this helper struct, we can verify that I have number must implement the trait has numbers. The whole point that we have here, if I remove that, we will get an error, obviously, because it doesn't satisfy the requirements of this trait. Yeah. Um, it really, the whole point is that this code is now running at compile time, not running at runtime. And this is what's possible with constant function evaluation here in Rust. Granted, you will probably not write this code very often, code like that, but it was just an introduction for what we can really do with this constant evaluation of functions at compile time. So let's dive right into the next example, which goes into exactly the same direction. Let's copy here this sample code here. This is a regular function. This is a function. Let's remove the const here. This is a regular function generating 5 numbers. It does it rather strangely because we don't use a for loop here. We use a helper variable, a while loop, and just fill an array of 5 numbers with some values and return this array. The point why I do the for loop here is that I can put the keyword const in front of this function, 5 numbers. And by putting the const keyword here, we allow Rust to run this function at compile time when generating the value for a constant. And very important, we can also use it to initialize static members, static variables. So if you have static variables, we can also initialize the static variable with the result of a constant function. So what we can now do is we can define a constant with 5 numbers. Let's put it this here in the main method, and we assign the result of 5 numbers here to exactly that constant. This code does not exist at runtime. It is executed at compile time, and we have this constant, and the value inside of this constant is compiled into our executable and just read from the executable. That's it. So it's really a constant value. And the reason why I didn't use a for loop here is because for loop, unfortunately, are not supported inside of constant evaluated functions. It's not possible. Don't get me wrong, we don't need to use a constant here. We can also use a variable. So constant functions are not limited to applying them at compile time. We can also apply them at runtime. In this case, I have a let, not a const. So I'm using the 5 numbers function at runtime. And now Rust will compile this function, put it into my executable, and I can use it at runtime. So this is what we see here. We can go one step further. Let me show you what we can do if we add a little bit more here. Now this method, numbers, is a generalization of 5 numbers. What it does, exactly the same as before, but the big difference is that the upper limit of the while loop here is passed in using a const generic. So the takeaway here is that const functions are very powerful. They can be generic, and they can even receive const generic attributes. And that gives us a lot of power, because with that, we can generate an arbitrary number of numbers in our case. We can declare 10 numbers as an array with size 10. Now Rust will call this method here. It will derive the constant generic argument directly from the type declaration on the left-hand side. So it will take the value 10 and use it as the parameter n in this constant evaluated function, and it will give us 10 generated values. So if I add, I don't know, 15, the constant generic will change, and therefore we will get 15 values. I think you can guess what's happening here. I can show you that. I can copy that one and maybe go into, for instance, not that one. Need a new browser window. Ah, that's the wrong one. This one I prepared. Let's put it here. Let's use the release build. This is the Rust playground, and I'm going to generate the assembler code here. Let's give it a second and I will scroll down. I will scroll down and here you see what I wanted to show you. Here we see 1, 2, 3, 4, 5 constantly evaluated inside the executable. And you can guess what we see down here. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be the 10 values. This is what I wanted to show you. This is really evaluated at compile time. So this is not a trick. Rust does it at compile time and writes the result of the constantly evaluated methods inside the assembler code, inside of our executable, and we can simply read it from there and consume it from there. This is what we do with this constant evaluations. Okay. I see we have some questions. Let me see. The first one we have to check. The second one, I think I clarified that. And Elvin is asking, are const functions not called in a const context really added to the compiled output? No, they are not. They are just added to the compiled output if I call them at compile time. At runtime, I'm sorry. At runtime. I hope I understood your question correctly. If not, please add the question again or rephrase it a little bit. I hope I understood it. Now, what can we do with this stuff? What can we really do? Where can this be useful? I created a sample which is a little bit longer and I will copy it in as a whole because it is a lot of code and we only have limited time. I told you that we will spend approximately half an hour on this topic, so I have to copy in a little bit of code. This example is inspired by crates like this one, consts, and you can take a look at it. It's just an example, and but I changed it, I customized it so I can really describe what's going on here. Let's first take a look at this function here. This function is called len, and what it does, it receives a slice of strings. We take these strings and iterate over the strings. Unfortunately, we cannot use an iterator here. Iterators are not supported inside of constant evaluated functions. That's not possible. So we have to use something else. We use slice deconstruction to, in a while loop, get the current value and the rest of the values inside the tail variable. And then we take the length of the current value and assign the remaining here, which is the right-hand side of this while let operation, to the tail. So with this, we have the full slice of strings, then we cut away the first one, second slice, cut away the first one, and we do that and do that and do that until we have no more strings left inside of the slice. And we calculate the total length of all strings passed into the length function. This is what this method does. And because we have written it in that specific way, we can decorate it with the const keyword here at the beginning in order to be able to run this method at compile time. Now let's scroll down a little bit and maybe you have already guessed what I'm going to do next. I'm trying to build a concat function that accepts a slice of strings and then concatenates all these strings, but doing that at compile time and not at runtime. Let's take a look at this example. It takes the various strings here as an input parameter and allocates a buffer of adequate size. We simply take the total length. We get that again through a const generic parameter. You see it exactly here. And then we have to write again a little bit awkward code because we are not allowed to use for loops. Yeah, but we apply the same tricks as before. We're also not allowed to use iterators, so we will do this this slice deconstruction again, this trick that we had before in the len function. we allocate the appropriate buffer. We had it before, so we can simply copy all the strings into the allocated buffer, as you can see it here. Again, no for loop, so please excuse this code. It is necessary in order to be able to make this method const. And at the end, we simply return a helper struct which contains the concatenated version of all the strings that we passed in here. This is what we do in the concat method. So let's try to apply that. Let me zoom. No, I don't think I have to zoom. Let's put it that way so I can draw a little bit. Please take a look at this line here. Here we are declaring a slice of constant strings which says hello world. Here, we are using a constant where we call the constantly evaluated function len, so we are calculating the total length of all provided strings in line 62 inside of another constant. Then we take here the concat buffer and we use the constantly evaluated method concat that you have seen a second ago in order to get a buffer, which is nothing else than, again, an array of U8 of bytes which represent the string. And last but not least, we use a method from the standard library from UTF-8 unchecked to turn it into a string, and we can print it on the screen. So at the end of the day, we were able to take all these constant strings and concatenate them to receive a single string at the end. And all the magic is done at compile time and not at runtime. Now, if we hover over here, over this from UTF-8 unchecked, it's obviously very important that this method from the Rust core library also has the const attribute here. It is also a const function, because otherwise we weren't able to use this function here in a const context. It wouldn't be possible. But with this, that is perfectly fine. And again, don't get me wrong here. We can do exactly the same, but this time at runtime. So here you see again our strings. We already have the len calculated. We use the concat method, which works perfectly fine at runtime too. We use the from UTF-8 unchecked, perfectly fine at runtime, works like a charm. But the const in front of the function allows us to use the function in a const context. Okay? So let's try that with a little bit of macro magic. My good friend Elvin convinced me that macros are super useful. So I tried to build a macro here that makes applying this len and concat function in a little bit easier. Elvin did a great talk about macros last time. So I tried to apply this knowledge directly here in this talk. So as you can see, this is exactly what we have done down here, but just written in a macro. This macro takes some strings as parameters, as you can see it here, and we are doing exactly what we did down here. But that makes it way more convenient. We can just say my concat, which is the macro, give it the first string if we want. Here, this is a const string. Give it here a literal, and give it here another const string. Some of you might say, hey, we don't need that because there is already a concat macro built into Rust. Yes, that's possible, but this concat macro that's built into Rust does not accept here constants. We have to, I don't know, do something like that and have to add the cat, and we have to add the, I don't know, mouse here. Yeah, it works perfectly fine. This works. This is built into Rust. We don't need a manual macro here. But I wanted to build, just for demo purposes, a version of a concat macro which is capable of referring to another constant, just for demo purposes. In fact, there are a lot of crates out there that contain lots and lots of helper functions capable of doing string concatenation, capable of combining strings with values, with integer values, and so on and so on. Just use your favorite search engine to look for crates that contain const functions that you can use in a const or static context. But I hope this example was somewhat useful for you to understand what we can achieve if we don't just write trivial code as we had it before, but a little bit more extra code, a little bit more advanced code that we can execute at compile time. Okay, now the latest and greatest versions of Rust added a bunch of extra things with which I would like to close my talk today. Okay, so the first thing that I would like to show you is the possibility to add trait bounds to generic constant functions. Let me copy in a little bit of code here. This one. Here we are. This is a little bit of code. Here we have the customer here, and we have a constant customer, nothing special here, works perfectly fine. Now we can, as I showed you before, define constants not just on top level, but we can also define these constants inside of the main method. And here I'm doing something a little bit different. I'm creating an array of two customers. We have the customer John and we have the customer Jane. And now I would like to write a constant function that takes the nth element from an array and copies it out here. And this is how you can do it. This is the constant function. And with this constant function, we can copy out the nth customer. Let's analyze this function. The constant function, the implementation is trivial. That's not the point. It gets an items array here with a constant generic parameter, and it gets the required index as the second parameter. But the important thing that you see here is that one. This is new. This is brand new. In fact, it became possible, stable, in Rust 161. 1.61 is the version of Rust that makes it possible to specify generic parameters for constant functions. Sorry, trait bounds on generic parameters for constant functions. This is new, and this is now possible. So if you need that, take a look at it. It works like a charm. The second example, which is new, regards to impl and dyn traits, to trait objects. So let me get rid of that example here. Here we are. Let me get rid of that example, exactly. And then I can bring in a little bit of code. And I'm going to show you what we can do with that. Now, this is a kind of classical example when it goes to polymorphism. Here we have a trait animal, which has a method make sound, which just returns the sound that each animal makes. We have a cat and we have a dog. The cat says meow and the dog says woof. Pretty clear. Nothing to do with constant evaluation or something like this. That's perfectly fine. Now let's add here a helper method, and this time it's a constant method, and this is again brand new for Rust 161. So if I add that one, you will see that this method generates my favorite animal, which happens to be a cat. We have two cats. And the new thing is the support for impl here. We can return an impl trait from a constant function. And that works perfectly fine. Let me show you how that looks like if we copy in the code into the main method. Here you can see that I'm calling this favorite animal constant function here. And then we can assign it, for instance, here to a trait object and then call it this make sounds directly here. But this favorite animal returns an impl trait, and that one is new. Just like returning an impl, we can also do dynamic dispatching. Do dynamic dispatching with something like that. In this case, I am implementing a method which is called animal by sound. I specify a Boolean value saying whether the animal has to be able to purr. If this is true, this has to be a cat. Otherwise, this has to be a dog. This is just for demo purposes. But the point is, the return value here, the return type, is a trait object. So we are returning a dyn trait object from this function. And that, again, is a brand new feature in the Rust version 161. And again, let me demonstrate that. It works like a charm. If we put it here, you see animal by sound, this returns the dyn trait object. We can assign it, and calling it works perfectly fine. Okay, so these were two new things that came with Rust 161. And I would like to close with one final demo that looks a little bit into the future. Let me show you this example. Sorry, I have to switch between my Visual Studio Codes. Here we are. Let me show you something here. And in this case, I'm doing that one. You all might be familiar with tricks for how to create a static mutex. I just opened up a Stack Overflow post, which is very, very highly appreciated by many people, and it shows how to use a new mutex, a static mutex. You see tricks like lazy static, using one cell, using many other possibilities, just tricks that you need in order to create a static variable holding a new mutex. And this is now no longer necessary. Let me bring in the type here. And as you can see now, with the nightly version of Rust, which might come with Rust 163, the new function and various other functions in the area of sync types are now const. So you can see it here. Mutex new is, it can be called in a constant evaluated context, and we can do that here. Let's put it that way, const. This is what I wanted to show you here. This is the const thing, and then we can also use it. Let me show it to you. This is my array, and here we are. This is the code. There it is. This is how we can use it. Now here we have the array. What did I do wrong here? Yeah, this is what I wanted to show you. Here we have a static value. I need to, of course, I told you, sorry, I'm not that good in typing and talking at the same time. Of course, I cannot change that to a const because it isn't a const. It should be a static. That's the whole point here. But I told you that constantly evaluated functions can be called not only in a const context, but especially in a static context. So here we use the mutex new, and it's possible because it is now a const. If we copy this one into our Rust playground, where is the Rust playground? I think it is here. Here it is. And we try to run this thing, it will probably not work. Exactly. You see that here we have the problem in the stable version that mutex new is not a constant function. We cannot call it here in a static constant, in a static context. But what I can do, I can change that one to the nightly channel and run it again, and it will hopefully work just fine. Yeah, it worked just fine. This is new, this is coming, and a lot of additional methods are now const methods, and they make it much easier to consume them in a static context. I can't say context today, in a static context, as I showed you in the sample. So my goal for today's talk, let me get rid of my screen here. My goal of today's talk was a quick introduction what Rust is capable of doing. I promised you that I would like to share my samples with you, and I will do that immediately. Give me a second. I will look it up here in my GitHub repository, and here it is. I will now paste in the link to the entire sample, including all the comments inside of the code, and I can also share another file with you, which I will paste on the Discord channel. So if you are on the Discord channel, feel free to grab the following links. I go to my Discord server here, and here it is. And I will show you that in a second. Give me a second. Okay, sent it. What I did for those of you who would like to take a closer look at these samples that I showed you in my GitHub, in the Discord server, I have created a link to every single sample that I showed you today. So I want you to be able to try all these code snippets. You can click on these links, and these links will bring you directly into the Rust playground in order to try with it, to play with it, to see whether I did something wrong or to extend my samples or whatever you want to do. So, this is what I wanted to share with you because I think if this is a beginner friendly talk, it is important for you to be able to try to play around with these examples. And that is essentially all that I have for you today. I promised you that it will take approximately half a minute to walk you through some new things that Rust is capable of doing in const contexts. So let me see if we have some additional questions here.